Okay, so what are we going to do? We're really going to refer to our boundary conditions that we have. Maybe I'll just keep scrolling back to those. These are the ones that that we have. So these boundary conditions here are going to form the basis of our discussion for what occurs at the surface, an interface between two media that have different properties. So there's epsilon 1 here. I should be careful. This is epsilon 2. Yeah. So we're going to start with this. Okay. We've seen that the electromagnetic waves in vacuum can be written in a simple plane wave form. If we look at monochromatic waves, they take a very, very simple form. So let's consider the following situation. I'm going to have an interface, and here I'm actually going to use the strange coordinate system that Griffiths uses here, because Purcell-Morin doesn't discuss this very extensively in the book, and I would refer you to the Griffiths discussion of this. It's somewhere in chapter 9. Anyway, the coordinate axes are x, y, and z in this way. Okay, and on the negative axis, you'll have an incident wave. Okay, so there's going to be an incident wave that's going to go like this, and it will be polarized along the x-axis and have a magnetic field along this. Okay, so there's going to be an incident wave like this, and so I will use straight the form that we had in vacuum for a monochromatic plane wave, now propagating in the z direction here as a function of time, and polarized along the x-axis. Okay, so what is this? This is this vector E0. Actually, it's not even a vector because we put it straight in the polarization x-axis. So this is going to be E0 incident, e to the I k. I'll put K1. Yeah, so K1 because it's in the first medium. So here on the left is going to be the first medium and then the second medium. At the boundary z is equal to 0, there's an interface between these two media. So everywhere on this side, it's got epsilon 1, mu1 characterizing it, and on this side, it's different things. So this is really an interface between two different types of material. Okay, so that's my incoming electric field. Now you remember that the magnetic field for a plane wave, it was k, the propagation direction, cross the electric field. So the magnetic field on this, here I'm really just like lifting the equations from vacuum that we have. It's going to be a function of z of t as well. There's going to be a magnetic field amplitude here, but this is really the amplitude of the electric field divided by the velocity. You can refer to the equation. So this is E0I divided by now the velocity in the first medium because we're incident here. Okay, and then the same spatiotemporal dependence here. But now this one is going to be polarized in the y direction. Okay, so you see you've got an EI here. You've got the BI here, right? So the pointing vector goes towards the positive z axis. Okay, that's where it goes. Okay, E cross B goes this way. So that's my incident wave. Okay. Now there are going to be two things occurring here. There's going to be a reflected wave, and there's going to be a transmitted wave. Okay, so the transmitted wave, we're going to use the same kinds of coordinates like this. So this is going to be the transmitted wave, and it will have an electric field like this and a magnetic field like this. There's going to be a reflected wave, okay, which will propagate the other way. And here, just as a kind of matter of convenience, we do it this way. So this is going to be the E reflected and the B reflected. Okay, so you see as my incoming wave comes, so it's got electric magnetic propagation like this, it hits the boundary and gets reflected. So now the reflected wave propagates the other way. Its pointing vector goes the other way. And then you got to make your choice for axes. You say, okay, well, we're still going to have the electric field like this, but now I'll put the magnetic field this way with a positive value so that my pointing vector goes like this. Okay, it's just really notation here. You can make different choices and get the same physics. However, now having made this choice, we can parameterize the reflected and the transmitted waves. And it's just a slight variation on all of this. So first of all, the reflected wave. This has an electric field, which depends on Z and T. But now, what is it? It's got some amplitude, E0R. It now moves towards the negative Z direction. So here, I got to change the direction of motion. So really, I have I, but now minus K in the first medium, Z minus omega T. So if this was a right moving wave, this is now a left moving wave. Okay, and the polarization is still in the x hat direction. The B reflected ZT. According to our conventions, you see I'm kind of measuring B now the other way around. So I've put a minus sign, E0R over B1. And now, again, it's got the same spatiotemporal dependence, minus K1 Z minus omega T. And now this is also in the Y hat direction. And finally, for the transmitted wave just looks very much like the incident wave, with the only difference being that the coefficients, permittivity and permeability, they are now those of medium 2. Okay, so sorry, this is not the I, this is transmitted. So this is E0 transmitted, now E to the I, now K2 in medium 2, Z minus omega T. Still polarized in the x hat direction, and the B transmitted, ZT. Again, it's the similar construction here, except that we are now in medium 2. So this is V2, E to the I, KZ, K2Z minus omega T, Y hat. Okay, so this is, if you want, my ansatz for the waves that I have. Okay, so there's a kind of lot of things I'm putting by hand here. If I made different choices here, I would get different intermediate steps, but the same physical conclusions. This is a parameterization for the waves that I've got present here. And with this chosen parameterization, then we'll write equations relating these amplitudes for incident, reflected, transmitted waves here, based on the equations that we've had. Okay. So that's where we start. Now, what's our game? Our game is simply to satisfy the equations, the discontinuities of the field at the boundary, because that's all we've got. We've got the whole thing now solved independently in the one side or in the two side. Why? Because we've used this free wave form, monochromatic plane wave. And we know that the monochromatic plane wave solves the Maxwell's equations in that particular medium. So now the only place in space where we have not solved the problem is at the boundary between the two. Okay? And that's great, because that's exactly what will relate one side to the other. Okay, so that's what we're going to do. Yeah, so how does it go? Well, we invoke our equations one after the other. Okay, so maybe I go back here and I number my equations once again. So we'll do here 1, 2, 3, 4. And maybe I'll call them B1, B2, B3, B4, because these are like boundary conditions. Okay, so what do I have? Well, you see here, what B1 tells me is the relationship between the perpendicular components of the electric field. Okay, so so how does that go? Let's just see the perpendicular. So my surface now is the XY plane. The perpendicular components of the electrical field, okay, everybody's 0. So I've already solved that if you want. Okay, here I have no electrical field in the perpendicular direction to the plane. Everybody see this? Wave is propagating along Z. Okay, all the waves have an electrical field which is in the X direction. And the X direction is one of the in boundary plane components of the electrical field. But the perpendicular component, the Z component of the electrical field, vanishes throughout. Okay? Nobody has that. Therefore, B1 is automatically fulfilled because E1 perp is equal to E2 perp is equal to 0. Everybody's happy. Okay? The same thing with B2, because the magnetic field is in the Y direction, which is also an in-plane direction for our boundary. Therefore, B1 and B2 are automatically satisfied. So now the first non-trivial equation is B3, which now tells us that the in-plane, in-interface components of the electrical field have to be continuous from one boundary to the other. So what does that translate to in our setup? Well, it just means that on the one side, if so B3, it implies that the electrical field on the one side is equal to the electric field on the two side evaluated at the boundary. Okay, so that means that the E incident plus the E reflected, when evaluated at Z is equal to 0, for any X and Y, has to be equal to E transmitted, again at Z is equal to 0, for any X and Y. Okay, and I should take you know, so the in plane, yeah. So here essentially the parallel component of these things, but everybody's on the x-axis, so everybody's in parallel. And what this condition tells you really is that the constants are simply related. So the amplitude of the incident plus the amplitude of the reflected has to be equal to the amplitude of the transmitted. Okay, that's it. So you see here, if I'm evaluating, you see, so I'm putting Z is equal to 0, right? You had a question, maybe you kind of were wondering. So look, maybe let's do this, right? So here, let's use our replacements here. So the incident at Z is equal to 0. Yeah, you see, if I write it in detail, I'm evaluating the incident at Z is equal to 0. So you see this K1Z disappears. I just have this minus omega t. So this one here is just E0I e to the minus I omega t x hat. And then this one here is E0 reflected, again e to the minus I omega t, also x hat, right? And this has to be equal now to this other one here, which is E0 transmitted. Again, I'm using just this equation here, putting z is equal to 0, okay? E to the minus I omega t, also x hat. And you see, that's where this comes from. This is valid for all times. The only way I can fulfill this equation is if these amplitudes are so related. Is that clear now?
Well, right in my eyes because this transmittance portion is from the incident, so the incident would be larger, right, than the transmittance amplitude.
Oh, but be careful here because we haven't, this is not a measure of the energy content. This is only a measure of the kind of matching between the two. So you see, if you have the boundary here, then what it tells you is that what comes in here, the size of the electric field here has to be the same just on the other side of the boundary. Okay, and of course the size of the electrical field here is the sum of the size of the incident with the reflected one. But I never told you that one was positive or negative, right? So it could be that indeed in absolute value, yeah, this one is bigger than these ones. But this is just my parameterization for that particular thing. And then the precise values that these take will depend on the values of my my permittivity and permeability in the two media, right? So it's not a statement yet about energy transfer or intensity. Okay, so that's B3, and now B4. Before I remind you, it's 1 over mu1 B parallel minus 1 over mu2 B parallel 2 is equal to 0, right? So this one here. Okay, so now I will just use the same logic here. So what do we get? We've got 1 over mu1 B1, but B1 is really the B incident plus B reflected. So it's got these things, these two things here with that parameterization. So in our notations, this becomes 1 over mu1 V1, and then the incident bit just has this E0I. So it's just this E0I. And now with the reflected, we had put this little minus sign here, just again as a parameterization choice, E0R. So again, I'm kind of doing the same reasoning. It's the kind of parallel component, but I'm going straight to the Y component in this. So I'm writing straight the coefficients of the vectors here. This has to be equal to 1 over mu2 V2 with the E0 transmitted. Okay, so these are our two equations. Yeah, so there's this equation. Maybe maybe I call it little star and little double star. Well, maybe that's not so good. Yes. So and you can isolate. So it's now your choice, right? What are you going to rewrite in terms of what else? It's kind of natural to scale everything with the incoming, the incident amplitude here. So I'm going to write E0R and E0T in terms of E0I. Okay, so what you can do is just rewrite, say, this one here in a slightly more convenient manner, which is E0I minus E0R is equal to beta coefficient beta E0T, where this beta here is by definition the ratio of the mu1 v1 and mu2 mu2, and this is, if you can rewrite it in terms of the refraction indices. So the refraction indices are just 1 over these ratios of velocities, Okay, that's just a number that takes a certain value here. So if you solve these two equations, then what you get is that the reflected amplitude is equal to 1 minus beta over 1 plus beta times the incident one. And the transmitted amplitude is equal to 2 over 1 plus beta E0I. Okay, just a simple algebra giving you these relationships here. Okay, so this actually solves the whole thing. Now, if you tell me what amplitude the incident wave has, you know all the amplitudes for both the electric and the magnetic fields of the reflected and transmitted waves. Okay, so now maybe we can go back to some more physics in the last 2 or 3 minutes. So what does that mean? So what was the intensity of the wave? Okay, we had discussed this. So the intensity of the wave was really the kind of average of the size of the pointing vector. That's what the pointing vector does. Here, this average here means a kind of time average. Why time average? Because the wave oscillates. Okay. And what you're doing is that you're just averaging over a cycle of the wave, because the wave is beating like that, and you do the average of this, and it's like averaging cos squared over one cycle, which gives you a factor of 1/2. Okay, so your cos squared is your intensity in this. So what this was in vacuum was 1/2 the speed of light, and then epsilon 0 E0 squared. So we're not in vacuum. So in matter, this is the same thing, except we now have to use the wave propagation velocity v with the epsilon for that medium with E0 squared. Okay, that's the intensity of the wave. It's the amount of energy that goes through a certain unit area per unit time. Okay, so now we can consider the ratio of reflected intensity over incident one. Okay, and this ratio is the reflected intensity divided by the incoming intensity, and this is just E0R squared over E0I squared, and this we've calculated above. It's 1 minus beta over 1 plus beta squared. Okay, and this is really the reflection coefficient that you will have been used to. And similarly, the transmission coefficient, T, transmission coefficient. So this is the intensity of the transmitted over the intensity of the incident, and this one is really just this this combination that we had before. So you have to be a bit careful because there's a ratio of the velocities appearing here, coming from this definition here, where we change the things. E0 T squared over E0I squared And then, so this thing is 4 beta squared, but then this one is 1 over beta. So what you get is 4 beta squared divided by 1 plus beta squared, but then there's a 1 over beta. So this becomes 4 beta over 1 plus beta squared. Okay, and NB R plus T is equal to 1. Okay, so the energy flow that you have in there is partly incident, then it gets partly reflected, partly transmitted. But these coefficients, reflection, transmission coefficients, tell you how much energy goes in, how much energy is reflected back on these things. Okay, so this is, you then give me some epsilon 1 mu 1 for one medium, epsilon 2 mu 2 for another medium, and now you calculate the reflection transmission coefficients for that thing. So that's the way you do this. So this is the simplest case of just absolutely normal incidence onto a surface. There's a more complicated case of an oblique incidence. I'll see next time if I have time to discuss it a little bit. If not, it's in the notes.